Hi, this is Mrs. Gonzalez. I am going to go over the key features of exponential functions. So first, what I want you to look at is that this is our growth model. And this down here is going to be our decay model. They still have similar properties, which is important to understand. So before transformations happen, you are going to start at 1. That is our initial value because A is 1 before transformations. This is the same thing when we had all of our other types of transformations. The parent graphs always start with A being 1. So A is bx minus h plus k. Next week, we're going to talk about transformations and we're going to look deeper into it. Today, we're just going to talk about our basic key features. Here, basic key features, you start at 1, and your domain for all exponential functions are going to be all real numbers. That is not going to change. Every single function, growth or decay, is going to be negative infinity to positive infinity, all real numbers. Your range is going to be what changes, and you're going to have to take a look at it. The reason your range changes is you will always have a horizontal asymptote. Your horizontal asymptote is going to be equal to y equals k, whatever k is. You can figure, look at this exponential function. It is approaching 0, but it is not going to cross 0. There is no exponent that you can put on any base that is going to give you 0. Remember, 5 to the 0 is 1. If you go to a negative, 2 to the negative 1 was a fraction, 1/2. So no matter whether that power is negative or 0, it is always still going to be a positive value. So our range is going to go from 0 to positive infinity. Okay, the horizontal asymptote before transformations is always going to be 0. As I move that graph up or down, that horizontal asymptote could change. Pearson does a really good job of talking to you about the end behavior. I want you to take a look. They'll go over a slide and an example with end behavior written in there. I would like you to talk about that end behavior. Make sure it goes down into your notebooks, okay? Here's the decay model. What I want you to look at is how it doesn't really change that much. Okay, so here, the decay model doesn't change anything. My horizontal asymptote is still 0 because k was still 0. My graph is approaching that but not going over it. My range is still, I'm going up from positive infinity up here, so it is still from 0 to positive infinity. Because my smallest bottom of my graph is still 0 down here, and the top is positive infinity up here. Okay. Okay, so now what I would like to talk about is the end behavior. So the end behavior, if you remember, is as x approaches positive infinity, what is y doing? So that is asking on this side of the graph, where is my graph pointing? It is pointing up to positive infinity. So as my x approaches positive infinity, so does the y. On this side, where am I approaching down here? Well, if you remember, this side is approaching your horizontal asymptote. So one of your end behaviors are always going to be approaching your horizontal asymptote. It's going towards 0, but not going to cross 0. Okay, so decay is very similar, except it's the opposite. So as x goes to positive infinity, so as I'm out here, what is my graph approaching? Again, it's approaching 0. It's not crossing 0. So therefore, the smallest it's going to get is close to 0. Remember, with the end behavior, we're not reaching those values. We're not going to ever touch those values. That's where the graph is headed, but not necessarily going to reach. We can't reach infinity, just like we can't reach our asymptotes, but we're headed towards that way. Here is your negative infinity over here. Where is my graph pointing? Pointing up towards the sky, so it is pointing to positive infinity. And that is how we talk about end behavior of an exponential function.